here we are. Welcome to the Natural Science 116 first video lecture. And I'm doing this in my office, which I've organized as a little studio here. Chalkboard's a little small, but if we need more board space later in the coming days and weeks, we can go elsewhere where I have larger boards. But we're going to start with this one. Good. So let's start with some announcements here. First, I just want to discuss the remaining time we have in this semester. So I've mapped out the remaining lectures. This is today, actually the 24th. This will view tomorrow, but good. This is this lecture, the 24th, Tuesday. Then we have Thursday, the 26th, 31st, April 2nd. Then there's spring break. So I sent out that syllabus, and the exam that was up here has been canceled. So after spring break, we'll spend all of this hour on a review, because I want to make sure you guys know what's going to be on these exams. And then on the 16th, we have the exam. And as I stated in the syllabus, I'll email you the exam. By then you'll have a good way to take the exam, take a picture of it, email it back to me in a form that I can print out and grade it like the usual. So good, we'll have that. So yeah, that's 1, 2, 3, 4 lectures of new material, review the exam. After the exam, it's similar. 21st, 23rd, April 28th, April 30th. Those are 4 lectures. And then the last day of our semester is Tuesday the 5th. Wednesday is the last day of lectures altogether. So Tuesday the 5th, in which we'll also do a review. Consultation days. Of course, you can email me anytime. More about that later. Consultation days, and then this is the final exam, which will be in the same format. I'll send something out to you. You'll print it out, take the exam, get it back to me by email in one form or another. If you're taking pictures of these things, you want to make sure I can read them, print them out and read them. Yeah, so that's the rest of the semester. Material here, heat engines, so thermal physics through heat engines. Heat engines. Okay, that's the material here. Down here, electricity and magnetism. I'll just write electricity, motors, the grid. Yeah, we were shorted this semester anyway. We had fewer hours to start with. Now we've lost a week, and we're losing some time, but don't worry about that. We're going to have some good material that will get you guys your money's worth, so to speak. Yeah. What else here on our announcements? So those are the remaining lectures. The exams, like I said, will be very thoroughly prepared on these review days. So there won't be any surprises, but it was the same as the last exam. You're going to have to dig in and know something and write it down. The in-class paper is the exam that I dropped. Okay, I dropped the in-class paper, and when it comes to our book, I'll say a little bit about that as well. So the next thing I want to talk about is taking notes. Taking notes has become a major portion, a greater portion of your grade than before, because I'm not actually able to grade your book. Now, the book is still one of the most important parts in my mind. You were supposed to be able to take that thing out, and actually it would help you teach. It would help you teach a lot, because it should have been full of all kinds of interesting stuff. We're going to try to maintain that right? We're going to try to maintain that ambition. So when it comes to taking notes, after every lecture, so due the 26th, due the 31st, due April 2nd, due on the review day, is that you show me that you took some notes by laying them out on the table and taking a picture of them and sending them in. So we want really good notes. You're able to review this lecture, this video, more than once. You're able to stop it. You're able to write everything down and then some, put in some words. So your notes can and should be really good. And as you see, I'll also recommend printouts like we did before, so that this thing here becomes colorful and interesting. So I'll recommend some printouts that you can do for your book, as I've been doing in the past. So that covers the notes, the book, which is still our project, but like I said, I can't grade you for this, so I'm going to grade you for having taken notes. So those due dates every time. Now, for the exam, not. You'll see what I wrote on the syllabus. So most of these days here are also a due date for notes, but not all of them. Good, so you turn those in, take a picture. Once again, you lay them out on a table, so you don't have to have a picture of every page, maybe 4 pages at a time, you know, and send it in so that I can read it. I'm just checking off that you did it. Okay. Good, so I'm about to erase this. Yeah, I'm not able to edit these videos, so this is all one take, right? I'm just gonna keep going until we're exhausted here. Okay, so those are our announcements and what we're planning to do for the rest of the semester. Oh, I am sending these, of course, to my YouTube channel. And I'm going to send you a link to the playlist. Each one of my classes is organized as a playlist. I'll send you the link to the playlist, and then every time something comes up, you'll be notified, or however that works. I've never been a YouTube subscriber myself, but I'll send you the link to the playlist. That way you don't have to search for it every time. And I'll try to put these in twice a week at least, and that's going to be the start. You guys can give me feedback via email anytime you're sending these things in and anytime you want to. Good, I think that covers that for now. Oh, one more thing about taking notes. So when you're taking notes, right, you're basically just writing down everything that appears here. Leave plenty of space. Leave plenty of space. You can go back and fill things in. Also, I'm trying to present this as logically as I can. You leave some space, it'll be more logical in your notes than it is on my board. So leave plenty of space when you're taking those notes. Good, so the next thing we're going to do is a review. Where's my eraser? Here we go. Review of thermal physics. See how long I can keep these numbers in place or in order. So 3 is review of thermal physics. Yeah, here we're going through this thermal. Here we're going through the logic of the whole subject again, and probably going to be most of this discussion here today, in today's hour, is just to do that review and put it all into context. Okay. Check the time here. Yeah, so where do we start when we're talking about thermal physics? We had previously what's called mechanics. You know, and we had ended with force work, energy. Okay. Then we started in with thermal physics. And the progression went like this. We start with just the sensation of hot and cold. Right? This is, of course, in your notes. Go ahead and do it again. Sensation of hot and cold. That's the primary basis of the whole thing. We have sensation of hot and cold. We then find some phenomena of hot, cold. In particular, thermal expansion. For which we have interesting demos. Okay, so thermal expansion. That leads us to the ability to create a thermometer. Namely, something that responds to the temperature, or I didn't get the temperature yet, did I? Something that responds to these hot, cold states by expanding, contracting. And so when we get a thermometer here, we can then get temperature scales. So, right, this is the order. You have the phenomenon, you have some kind of thermometer, then you can create a temperature scale. And, you know, we have degrees Celsius, degrees Fahrenheit, and Kelvin, which is just capital K. So we have these different temperature scales. Yeah, thermometer, I could say including gas thermometer. Gas thermometer. But I won't stress that much. It was a discussion that leads from the gas thermometer to the Kelvin scale. So you get your temperature scale, and only then, and am I going to write down? Yeah, so temperature in Kelvin, temperature degrees Celsius plus 273. We have that definition, of course. At this point, we can talk about heat. Okay. Here we haven't really talked about thermal energy yet. Well, with hot, cold, but thermal energy. So the next thing here is thermal energy. And we can define the calorie. So I'm going to say a little more about that. We never got all of our demonstrations that I had wanted to show you, in particular that butter candle. So I'm going to go ahead and discuss thermal energy, the calorie, the butter candle. Okay, so we've got the calorie. And look up and know that definition. Here, I'll write that out. Know the definition of the calorie. Raises the temperature of a kilogram of water by 1 degree Celsius. That's what the calorie is, capital C. That's also the food calorie. Okay. So now let's go ahead and I'm going to assign actually the butter candle. So since I'm numbering these things so systematically, I'm here at 5 calorie definition. Let's go ahead and erase. And erase all this. Let's start with number 6. So 6. Butter candle demo and project. Now I was going to bring it into class, and now we ran out of that possibility. So how does this butter candle work? And what does it have to do with calories? Well, nothing epitomizes calories more than butter. Okay. Butter has calories. And the definition that you're going to have to be well aware of, okay, memorize that definition, look it up in your notes, remember it. So the definition just involves heating water. So what we do is for the butter candle, here I'll put little stars here, we need cotton string. And it's going to work as a wick if it doesn't actually burn up like nylon string does. So you need some cotton string, possibly cotton yarn would work as well, but it has to be cotton, can't have nylon in it. I don't know about wool. You'd have to try that, be an experimentalist. So you need cotton string. And here's your stick of butter. Okay, here's your stick of butter. You lay the string over the top and push it right into the butter. You can seal the top off, and now you've got a string that's embedded in the butter. You've got wick coming out here and a wick coming out there, and then you stand it on end. Put it on a little dish maybe, that's nice. And there's the wick. Make sure the wick is nice and soaked in butter, and you're going to light it. You'll get a little flame. Now the rest you don't actually have to do, but if you put it on a stand and had a beaker of water with a thermometer sticking out, you could say, yeah, there's my calorie butter candle project right there. Okay, so this picture here exemplifies what the whole definition of the calorie is all about. You're burning this food substance, it's raising the temperature of water, ignoring all the losses that are going to the side. There you have it. Okay. Now, so demo and project. So what I'd like to see if somebody did this at home and took a picture of it and was able to send me the picture, and better yet, not only send me the picture, that's easy to do, right? Print out the picture and put it in your book. How about that? Print out the picture, put it in your book, and you've got a really nice project, the butter candle. So when I'm talking about this project, do the experiment, take the picture, homework. We'll call that a homework project. Take a picture, send it in, put it in your book as well. Okay, that'll be nice. You'll impress everybody if you can make a butter candle. Okay, good. So that really exemplifies calorie. Now let's see what we have going on here. Ah, yes, good. So that was 6. Now I'm going to move to 7. And got the picture there, you know what to do. After you've burned it, just pull the wick out from the blackened end carefully, and all the rest of the butter is usable. No waste of food whatsoever. Good. All right, I'm gonna erase this. And we're on to our 7th point. So now we have the definition of the calorie, we have this beautiful project here, and now we're on to the mechanical equivalent of heat. So, mechanical equivalent of heat. Okay, this is going to be a question on the exam, without a doubt. Discussing the mechanical equivalent of heat. What is it? How do we determine it? Well, Joule churns water, which raises the temperature of the water. raises its temperature. Okay. So churning the water, that's work. Raising the temperature, that's heat. So you can convert work into heat via friction, i.e. work into heat using by way of friction, internal friction of the water. So that's what mechanical equivalent of heat is all about. We're turning work into heat just by the definition. In other words, you don't have to burn a candle and heat the water. You can just apply work on the water and heat it up as well. So what Joule finds out is that 1 calorie, by the definition we just have talked about, is equal to 4,186 joules. So heat and work. And when you discuss this on the exam, you want to be able to discuss everything we had on the board previously, because that's what calories are all about. And over here, you can discuss mechanics. In other words, force, work, and energy, because we have the Joule expression right there, okay? So this is a very key discovery. Very key discovery, mechanical equivalent of heat. We'll see later that it allows us to plan how much work we can get out of a given amount of fuel. So it's absolutely key for the whole civilization. All right, mechanical equivalent of heat. And let me add here as homework, and you may already have done this, namely just to get some images of Joule's churn. You're going to be able to do everything in this project just sitting there at your computer, except for the butter candle. That needs a little practical work as well. So images, if you already had them, show me that you have them, but get some images of this Joule churn thing for your book. Okay. Good, mechanical equivalent of heat. And what comes next in this progression? Yeah, once we have the mechanical equivalent of heat, we can define, I'll leave that symbol there. We can define the specific heat capacity. So that was 7, I'm going to go to 8. Notice this is all review, but it's good to hear it often, and always the progression and the connection is so important. So we have number 8, specific heat capacity. And the idea there, once we know this and we know the definition of the calorie, we imagine putting some heat and energy, call it Q, into some object of mass M, temperature T. And what happens? You put heat in an object, friction, butter candle, whatever, you're going to raise its temperature. And here's our formula. Put heat in, change the temperature, raise the temperature. In fact, you can lower the temperature and take heat out as well. Okay. So put heat in, raise the temperature. So heat in, raise temperature. And the specific heat capacity is this letter C here. This was an assignment, it could have been one of the last assignments that I gave, so you want to make sure you have it or can do it again. What we wanted was, first of all, the units of specific heat capacity were joules per kilogram degrees Celsius. And the homework here, like I said, past homework, you may have done it already. Print out a table. You can find something online, I'm sure, of specific heats. And since they use different units, you want to print out the table that uses joules per kilogram degree Celsius as the unit. Example, specific heat of water is 4,186 joules per kilogram degree Celsius. So if you get another half dozen specific heats or whatever you can find tabulated online, that's what you would want to do. Okay, I think we're getting towards the end of our review. So ninth in this list, I'm going to erase this now. Ninth in our list. 9. Heat transfer mechanisms. And that's what we ended talking about. We had what? Conduction, convection, and radiation. I don't think I had a chance to show you these interesting demonstrations we have. And that's too bad. I could possibly make that up for you if I take this operation to the lecture hall where we have demonstrations. We'll see. So conduction, convection, radiation, very important in all three of these cases. I like this cartoon here. We have two objects. One is at a higher, one is at a lower temperature. The energy flows from higher to lower temperature. That's a law of nature. Okay? Energy flows from higher to lower temperature. If you put these two objects in a cooler, close the lid, energy is going to flow from this one to that one. Eventually, they'll both be the same temperature. Okay? And the way this happens is by these three mechanisms, either conduction, which is direct contact, molecular collisions, or convection, which is a fluid flow like a breeze or a water current carrying heat much more efficiently, by the way, than conduction, or radiation, which is actual light, electromagnetic radiation of all wavelengths. Okay, so that's the kind of thing where I'm also going to want you to be able to give the definitions. Definition for each one of those three and examples of each one of these three. Like if you grab something hot in your hand, you're feeling the hot object because heat is being conducted from that object into your skin. Okay, that's an example. If you have something cold in your hand, heat is being conducted from your hand into that object. So in either case, this little cartoon works just fine. Okay, so heat transfer mechanisms. This is the kind of thing where if we're together in the lecture hall and we have the demonstration, we can go on and on with interesting examples, and I'm thinking I must have given some already. Not as much as I would have liked to. So yeah, look into that. I know you have it from natural science already. You've probably talked a bit about conduction, convection, and radiation. Okay. So now we have, well, maybe I'll actually say a bit more about this. There are so many great examples. There is one of the great demos. Let me just describe it. We have these two identical little blocks with a little bowl shape cut into them. identical blocks, and this one is wood, and this one is aluminum. They're stored in the same cabinet, right? They sit on top of each other. But if you take them out and grab them, the wooden one feels much, much warmer. They've been stored at room temperature. The wooden one feels much, much warmer than the aluminum one. They have exactly the same temperature. Why does the aluminum one feel cooler? Because the conductivity of aluminum is so high that the heat just flows out of your skin into the aluminum, okay? Does not flow out of your skin into the wood nearly as rapidly because the wood is more of an insulator. So the next interesting demo is that we put, that's already pretty surprising, we put a little piece of ice, maybe this would be a good one for me to demonstrate to you guys on, on film. We could do this. Put a little piece of ice on each one. In the classroom at room temperature. And now what's warmer? Of course, these are both at room temperature. The ice is quite a bit cooler. And what you see is that this piece of ice on the wood pretty much stays unchanged for minutes. Okay. Barely wets the wood. This aluminum, this ice on aluminum will actually melt down so fast that you can see the ice just disappear in front of your eyes and turn into a little puddle of water. Because the aluminum is now at room temperature much warmer and the heat just flows into the ice. Okay. Pretty dramatic. If you're into that kind of thing, right? So, important example of heat transfer mechanisms. Another example, if you walk across the carpet at night, or middle of the night, barefoot across the carpet, it feels warm. You go onto the tile floor, feels cold. They're actually both the same temperature. So again, similar example to this, having to do with the conductivity. So heat transfer mechanisms, thermal conductivity, the conduction right there. Okay, so that takes us as far as we had gone, and I've been a little more thorough, so we have some assignments to do, and let's see where we go from here. So here I'm just going to write down remaining topics, and by that I mean remaining topics for the next 3 lectures. Okay. Now that we have the heat transfer, we're going to talk about states of matter. Solid, liquid, gas, plasma if you want. States of matter and phase transitions. States of matter and phase transitions, that'll be a topic. And once we know about this, I think we have everything in place. Well, okay, there's one more very theoretical topic called entropy. Okay. I'm just going to write theory here. That's an interesting thing. We've learned about some abstract things before. Energy itself is an abstract concept. It's not a thing, it's a relation between things, capacity to do work. And entropy is also an interesting concept that we need to some degree. So states of matter, phase transitions, got some good examples there, entropy, and at that point we can finally get where we wanted to systematically be, namely talking about heat engines. Heat engines, that's our big goal up until the midterm, is to do all these things systematically. We've done things systematically so far. I'm not too worried about it. We want to get to heat engines and a good understanding of them. You know, why do we have to put gasoline in our car to get it to drive? Okay, it's a heat engine. It burns fuel. And the whole thing is, the fuel has thermal energy. There's a mechanical equivalent of heat. We can get work out of it. The work is the car actually moving up a hill, and on and on. So that's outline of our goals for the next 3 hours. Okay. Okay, good. I'm gonna end this hour right now. Send this to my YouTube channel. I'll be sending you guys a link to the playlist and all that once I get this thing going. Good.